Let's look at some diode limiter circuits, also called clippers. Um, so in the first problem, we have the input is a square wave, and sometimes it's a little easier to see with a square wave what's going on than to jump in with the sine wave, but it's pretty much the same thing, but it's a little easier to visualize with a square wave, so I thought I'd start with that. So let's just talk about the first thing you always want to do is to identify when the diode is on, because at that point you're going to have current flowing through the diode. So that's pretty important. So we know that we need to get above this barrier potential of 0.7 volts on the left side of the silicon diode on the anode side. So it looks like pretty much anything in the positive region above about 0.7. Again, we're talking about a practical diode, not an ideal diode here. So anything above 0.7 looks like that's going to turn on the diode. And since it's a square wave, it's going to be 12 volts there consistently until it changes direction. So if it's a positive 12 volts here, and we drop 0.7, that's going to leave the 11.3 volts across from this point A to ground, which I'm going to mark at B. So what we have essentially is a voltage divider between the 2.2K and the 1.8K resistor. So I'm going to use the voltage divider rule to figure out what the voltage would be across this 1.8, because remember, that is really what V out is. Okay, so the voltage divider rule, if I'm going to call this R1 and this R2, then V2, which is V0, is going to be R2 over R1 plus R2 times whatever the total voltage is across that divider circuit. So V2 is going to be 1.8K over 2.2K plus 1.8K times the total, which is 11.3. A lot of students make the mistake of saying that would be 12, but it's not 12. 12 is the voltage you're supplying to the input, but then we drop 0.7 volts across the diode, and we're left with, across those two voltage divider resistors, is 11.3 volts. So be careful that you don't make that mistake. So the portion of the voltage that we see dropped across that second resistor, R2, is about 5.085 volts. And that is actually where our output will be once we get over the 0.7. So that's going to be in this positive time. I'm going to draw maybe a little dashed line here just to kind of line them up. It's also helpful sometimes if you draw your V out right under your V in. That might help you with the sketching. And we're going to put this, we're going to label this at 5.09 volts. And then let's look at what's happening once we switch to the other side and we're at negative 12. What's going to happen when this becomes negative 12 is that all of a sudden our diode would be off at that point, because now we have a lower voltage at the anode than we do at the cathode, and that is not going to work. So what happens if this diode is off is that we essentially have an open circuit from the input to the output, so we don't have an output. So we would just be at 0 here. And that is what our output would look like. We would have a pulse at 5.09 volts, and then we would be at 0. And then if this is a periodic waveform, which it probably is, it would just kind of repeat after that. Okay. And that is the output that we would have for that circuit. Okay, so now let's look at a sinusoidal waveform. Again, it's not that much more difficult. I just wanted to start with the square wave because that will kind of help you see this as well. All right, so this is a different kind of limiter circuit. So for this circuit, we're looking at the output voltage in parallel with the branch that has the diode in it, and the diode is actually has a biasing of 4 volts in that same branch as well. So what we need to do again is identify when in our input waveform would that diode be on. Okay, again, remember it's a silicon diode, and we need 0.7 volts from the anode to the cathode side. So when would it be on? Let's say this is ground down here. We're assuming that's ground. Going from ground up across the 4 volt source, we're adding 4 volts there. And then to get across the silicon diode, we would need to have 4.7 on this other side here. So 4.7 volts will be when the diode is on. Okay, so that means that we basically need whenever our waveform is above 4.7, the diode would be on. Okay, whenever it is below 4.7, the diode would be off. Okay, so what does that do for the output? When the diode is on, then V out, let me write this over here. Okay, let me try that again. When the diode is on, then V out would be equal to the voltage across the diode plus that 4 volts, because it's in parallel with that branch. And when the diode is off, we don't have, we have an open circuit at the diode, but that open circuit is in parallel with V out, and there is still a path to get from the input to the output, and both should have a connection to ground as well. So when the diode is off, then V out will just be equal to whatever V in is. So if I go down here to draw what my output should look like, it's going to basically clip off everything above 4.7, and it's going to keep everything else, okay, because under 4.7 volts, let's see, greater than Vn greater than 4.7 volts, then V out is just going to be that 4.7 volts. Okay, so let me see if I can draw this here. Okay, it's going to clip right there, and then on the On the negative side, actually anything under 4.7 volts is just going to be the same waveform that we already had. Okay, so minus 8 volts, and up here this would be a positive 4.7 volts. And that would be your output. Okay, let's look at slightly different one here. And it looks like I have left off the fact that this is 3 volts here. Put the biasing in a different place because I thought that would be interesting to see. Got the same input waveform here. So again, what we want to do is figure out when is the diode on. Okay, so the diode would be on, again, we have to have this 0.7 volt drop here. But we also have this 3 volt drop across across the voltage source. So if we start at V equals 0 here and we add our 0.7, then we have 0.7 volts at this point. And then going back to the left, we would add 3. So right here, we would have 3.7 volts. So we would need the VN diode is on, having trouble writing this today, is on when Vn is greater than or equal to 3.7 volts. I'll just say greater than. And when the diode is on, then V out is going to equal that voltage across the diode, because V out is actually in parallel with just the diode. So it would be 0.7 volts for everything where Vn is above 3.7. So where's that? That's somewhere like right in here. So right at during this time here, I'm going to draw this down here and just kind of, like I said, it's a good idea to line these up because we're looking at the time. Now remember what I set up here is that when VL is greater than 3.7, V out is 0.7. So that actually shifts this portion down here to 0.7 volts. That's going to be where that is limited on that side. Now, let's talk about when the diode is off. Okay, so the diode is off when VL is less than the 3.7 volts, right? And at that point, you might say that it's just whatever Vn is, but it's really not, because remember, we've got this minus 3 volts here from the input to the output. So it's going to be whatever Vn is minus 3. Now the easiest thing for me to do is just to, like I said, line everything up and draw the waveform so that it looks pretty much like what we had here. That's a little more of a triangle than it ought to be. Let me see if I can make it a little less of a triangle here. It should be a sine wave. Now, so when you look at this -8, when we have -8 volts here, if you just look at the negative peak there, -8 minus 3 means that V out would actually be -11 at that point. So we're going to have a peak down here, a negative peak at -11. And on the top side, it's going to be limited at that 0.7. Okay. And that's kind of what happens when you add this biasing before you get to the branch that has the diode in it. Okay. And those are just a few limiting circuits, and I hope that you can go back and review this if you need to do so.